Rafał was not able to say the presentation with me, but he will be here after the session. So if somebody will have very low level questions, he will be able to answer it to you. So at the beginning, I will introduce you our problem on the basis of PL grid infrastructure example, and then I will show you the VeilFS system, its architecture, the user point of view, and the administrator point of view. Next, I will be talking about the things I think most interested for you, the technical issues, the techniques we used, the problems, and the classes of these techniques, and at the end I will conclude my speech. Okay, now we have increasing number of powerful computing infrastructures, such as grids and clouds, what causes more difficult problems than just increase of overall data volume. First, we have a variety of data, and we need a lot of computing power to get some really useful information from such huge amount of data. The increase of number of infrastructure causes also the increase of number of users, and many of these users are less technically advanced. For example, in PL Grid project, we have over a dozen domain grids, which are services for different groups of Polish scientists, for example, from astronomy, biology, chemistry. As you probably know, the people connected with biology or chemistry are not computer scientists, so many things are difficult for them. We have a lot of groups of users, so we have also to provide different storage systems and services needed by them. And it is usually impossible to do it in one site, in one computing center. So often the users have to do their computations using many computing centers, because one service is one center and other in the center at the other part of Poland. And it's really difficult for less technically advanced users. Let's see example to understand it better. The PL grid infrastructure contains 5 biggest supercomputing centers of Poland. Each of these supercomputing centers is at the top 500 list of most powerful computers in the world. So we have really a huge amount of computing power. This computing power is located at many worker nodes, which do computations. We have also a lot of storage types, for example, LFC, DPM, Lastre, and so on, connected to this worker node. Of course, we have users with their PCs, from which the users upload the input data, and we can also have some third-party services for archivization. So where are the problems for less technically advanced users, for example, scientists with biology? The problems are from the beginning, because when they want to do some computations, they have to upload the input data to worker nodes. It's not just simple CP. They have to use special job description files to show which input data should be copied. The structure of these files is not intuitive for many of users. Moreover, if the users want to perform their computations in many computing sites, because services are not at one place, they have to use special type of permanent storage. The data management with this permanent storage requires not easy to remember commands. So this is another difficult point for them. And of course, if they want to archive some data, they have to know external services API. Another thing to remember. So to sum up the problem, the users are typically interested in results. They want to manage data as if this data was on their local PC, because typically biology or chemistry scientists understand things that goes at their local PCs, and not many more about computer science. But on the other hand, we have administrators who are interested in effective utilization of resources of the computing centers. And they want tools that help them with data management that provide this effective utilization. So how we can do it to be good for administrators and users? So to do it, we have created VeilFS. It's a meta-file system that based on Fuse, which separates user point of view and administrator point of view. Users see the only logical namespace, which is translated to the real data location by Fuse. So the administrator is able to migrate the data anytime he wants. The user does not see it. The Fuse connects with the special data management components that makes the mapping from logical location to the real location, and then tries to write the data locally, because most of worker nodes are connected to most storages. Of course, if we have something hidden by Fuse, we can also copy the data from the other centers if it's needed. So the user even does not know that he operates at data that is really located in other center. So from the user point, everything is really simple, because he uploads the data at any interface at any computing center, and then this data is available at any worker node. The user can also mount the VeilFS at his local PC and then operate the data as if it was local, or just or simply use internet browser to manage all the data from all the grid from many computing centers. The scientists are also interested in data publication and cooperation, so we support it. The user can simply choose the data to publish, generate URL for this data, and send this URL to coworkers, and they are able to download the data using the URL. Of course, if it's needed, the user can stop sharing the data. If the user wants to cooperate with better with some friends, they may create a group. For groups, there are automatically created spaces, and the user can just throw the data to the space, and everyone from the group can edit it, can work on it. Many users are also interested in metadata, so we support metadata from the internet browser as well as command line. What I have shown you, it was the user point of view. It's currently in test, it's ready, and now we are working to develop some tools for our administrators. We want to give them advanced monitoring tools that monitors not only infrastructure but users' activity monitoring, and automatically detects failures and visualizes everything in one place. We want to automatize rule management of data using simple rules. However, I think now it's the interesting part, when you know the problem, when you know the product, the key mechanism that we use. As I said before, we have used Fuse to hide everything because the Fuse gives really low overheads. We do have some experiments, and we have written the data with Fuse in the similar time that without Fuse. the difference was 2 to 5%, so it's nothing. More interesting, I think, it's server side, because in the grid we have thousands of worker nodes. At each worker nodes may work many processes of users. We have external laptops of users. Everything connects with the data management machines. So the data management machines have to be able to handle thousands or millions of requests per second. So we had to choose really good and scalable technologies. And we have chosen Erlang, because if you are here, you probably all know that Erlang gives us massive scalability. For example, the web servers written in Erlang can handle much more sessions than similar web servers written in Java, and the difference is really huge. The other key question was the database, because it is we will probably have billions of metadata about location of data. So we have chosen noSQL DBs because they are very scalable, and adding additional nodes gives us more performance, more requests per second that we can handle. For critical low-level operations, we are using the C language because it's from the years very, very good to it. When we have chosen technologies, we had to think about the request flow. It's the key mechanism of our system because the number of requests is huge. Moreover, not each module of the system is able to handle only some types of requests, and the types of requests generated by clients changes with time. So we have to think very carefully how to resolve this problem. First, we have created something that is called worker host, that's based of Erlang servers, and that is able to handle any module of our application. This worker host starts request processing always in a new thread, because threads of Erlang are very light, so we are able to do it. So we have really massive parallelism. But massive parallelism is the one thing, but changing types of requests in time is other problem, because we have to be able to add and to kill instances of module live. The client have to send the request to particular module. So we are using a DNS server to show him where this module is. But validity of DNS answer is about 60 seconds. So in the meantime, we can migrate, add, kill module. So we have created dispatchers at the entrance of each node that are able to check if the module is at this node, and if not, they can forward the request to other appropriate node. It was very simple in Erlang, because creating of multi-node, multi-process communication in Erlang is as simple as created of simple program in Java that has one thread. So the Erlang greatly helped us in this task. Of course, we have used other advanced features of Erlang technology. First of all, Erlang supervision trees gives us safety and stability. I will be talking more about this later. Erlang has also code hot swapping, because when we are thinking about the system that have to be available 99.99%, we cannot just simply stop this product to upgrade code, because in grids we have jobs that are running for hundreds of hours, and if we would stop the system even for a few seconds, the hundreds of hours of computation would go to trash. We cannot do it, and Erlang gives us this great opportunity to upgrade everything when system is running. Of course, due to choice of noSQL technology, all components are scalable, even the database. But no one is perfect. So I was talking about that Erlang is great, noSQL is great, everything is great. Yes, but there are also some problems with choice of Erlang and non-SQL technology in cases of safety and some performance of some operations. Okay, when we think about security, we have to think also about stability. The program has to be stable and safe. So when we are thinking about stability, the Erlang is really great, because it has supervision trees. So our application that contains very many nodes is created like this, that at every node, Erlang application is going. This application has a supervisor which supervises modules. Each request is handled by new process. So crash of request won't crash whole the system. Even when module go down, supervisors make it up. We have added also a central point to manage this cluster of machines that is base of Erlang distributed application. Erlang distributed application gives us that if a node, when this application is going false, he will automatically raise it at the other node. So it is not a single point of failure. So using Erlang, we have fault tolerance at the level, at the request level, at the node level, because the node is supervised by the supervisor at this node. So when the network goes down, the node can work, and after the network goes up, he is able to connect to the central manager once more and ask if he should change some modules. And of course, we have this fault tolerance and the distributed central application of Erlang. But it's great when we are thinking about Erlang to Erlang communication. But we have clients from the outside, and we have to authenticate them. So the clients sometimes sends very, very important scientific results. They want to publish it first, so nobody can read it. So we have to secure the communication using the SSL. And we are thinking about scientific installation. We have to support grid security infrastructures and OpenID. And here the problem starts. Because we haven't found a good product in Erlang that support X509 certificates extensions. And it's very, very important for the grid. So we have to think what to do with it. We could write it from scratch, but it's a lot of work. We can also get some C libraries and just use it for Erlang. We thought that is a great idea. It's a good idea, but not perfect. Why? Because starting the external libraries, as well we have done it during the I/O interfaces from C, have some problems. Because we can do it two ways. We can start this code at the local virtual machine. it is very fast. But if anything in the library goes down, our whole virtual machine, our whole application crashes. And when we are thinking about 99.99% availability, we cannot allow that some errors in external libraries will crash all our application. So on the other hand, we can execute this code at the slave virtual machine. It's very safe, it's very stable, because when the library falls down, so we just move, give us a new slave, and everything is okay. But the performance of this operation is not as good as when we are executing the code at the current virtual machine. So we have safety and stability or performance, but not two. The other problems appeared in BigCouch. We thought BigCouch is written in Erlang, so everything should be perfect. Erlang in application, Erlang in DB, super. But BigCouch, although it's written in Erlang, does not provide Erlang API. So we could use REST API, but it's an unnecessary layer. The communication with database will be slower. So we had to write our wrapper on the internal Erlang BigCouch API and make BigCouch cluster a part of our application cluster to be able to talk with database fast. Of course, there are other obvious consequences of use of non-SQL databases. It's very scalable, but it's difficult to model some relations, and some relations, not many, are usually needed. And they are difficult to find the data when we want to find it not using primary key. So to sum up the technologies, Erlang and BigCouch are great products. When we are thinking about the creation of application that has thousands of or millions of clients, millions of requests per second, and everything have to go in parallel, Erlang is really, really great. But we have to remember that on the other hand, with Erlang and with noSQL databases, we will have some other problems that we have to make them. So to sum up, we have created and we are currently testing a meta-file system that hides the storage system complexity from user and integrates all storage resources in multiple data centers case. We have chosen Erlang and non-SQL, and after some time with these technologies, I can say yes, it was a good choice. They are great technologies, but please remember, no one is perfect. So Erlang also. So that's all. Thank you for your attention. Our key developer will be able to answer very low-level question after this session, and I will try to answer some questions if you have it now.
Okay, thank you. One question.
I have a question. You have chosen noSQL, but the common problem with noSQL is that it doesn't support transactions. It supports integrity only on a document level. Was it a problem in your application, or maybe it was irrelevant in your case?
Sometimes it's a problem, but in our applications, transactions was not as important as scalability.
Any other questions? Okay, so thank you once more.
Thank you.